So this reading is about physics on ice. A hockey player moves his arm, bringing up a hockey stick. He brings his arm down with an explosive force, launching the hockey puck at a speed that can exceed 160 kilometers per hour or 100 miles per hour. Hockey players do that all the time. The puck crosses the rink hundreds of times during a hockey game. What is unusual is that as it travels from one end of the rink to the other, the puck does not seem to slow down or change direction until an unbalanced force like an opponent's hockey stick acts on the puck. It seems like on its way to the other end of the rink at a constant speed and direction. Magic? No, inertia. Ice hockey is an example of Newton's first law of motion, the law of inertia or inaction. The icy surface of the rink reduces the forces that normally would slow the puck down, friction and air resistance. Smooth ice exerts less friction than rough ice, and rink ice is carefully maintained to make it as smooth as possible. Air resistance against the puck is minimal. Since these two forces, friction and air resistance, are so small, they do not significantly affect the puck's motion. Once in motion, the puck tends to move at a constant speed and in a straight line. Ice hockey is all about the speed and direction of the puck, which are made possible by the icy surface of the rink. Players and announcers of hockey games speak of fast ice, which has less friction, and slow ice, which has more friction. Very cold ice is fast. As a hockey game progresses, snow is shaved from the ice by skate blades and hockey sticks. By the end of the period, the ice is full of gashes and grooves, and a dusting of snow covers the surface. The additional friction of the snow and the imperfections on the ice make the puck lose speed as it travels from stick to stick or from end to end. Because of this additional friction, many players handle the puck differently at the beginning of a period than at the end. Careful attention is paid to restore the smoothness of the ice between the periods. An ice rink is about an inch thick, built from layer upon layer of frozen water at about -9 degrees Celsius or 16 degrees Fahrenheit, way below the freezing point of water. Once built, the ice is maintained by the resurfacing machines. Before and after every game and between periods, the ice is resurfaced to reduce friction. Ice resurfacing machines scrape off the snow, remove dirt and debris, and then lay down a layer of hot water. When the water freezes, it erases imperfections. After this process, which takes about 12 minutes from start to finish, the new surface is frozen and the ice is ready. Ice that has just been resurfaced is fast. On the other hand, ice that is frozen and refrozen, like the ice of rinks in warmer climates, is slow. It seems the melting and freezing move dirt and debris to the top layer. Ice that has melted and has watery film on its surface is slow as well. Can you figure out why? You can see a photo here of them resurfacing with the Zambino. If you've ever seen hockey, you've probably seen a Zambino before, and it's pretty cool if you watch them resurface. But why is ice slippery? Well, scientists continue to study what makes ice slippery. They all agree that the top layer of ice is responsible. Conventional theories are that friction or pressure of an object like a hockey puck or skate blade melts the top layer of ice on contact. The water created by this melting serves as a lubricant, and objects glide on the water that they generate. Most recent studies suggest that there are quasi-fluid or water-like layers on the ice, which cause it to be slippery. These slippery layers are not caused by pressure or by friction, but by the motion of frozen water molecules. In quasi-fluid layers, the water molecules move up and down only, not in all directions, as is the case with water. On very cold ice at about -157 degrees Celsius or -250 degrees Fahrenheit, the slippery layer is very thin. It is only the depth of one molecule. As ice warms, there are more quasi-fluid layers. Hockey pucks and players have to cut through these layers as they travel across the rink. Could this explain why colder ice is faster?